All right, this evening, Dr. Dale Partin is going to be speaking to us about the moon. He is going to cover the origins and substance of the thing itself, as well as mankind's relationship with it, including the funny parts. And Dr.
Pure
Partin,
lunacy.
Pure lunacy. Dr. Partin is a very accomplished applied physicist, as well as now a professional educator. So he will do some professional volunteer educating shortly. So thank you.
Can somebody cut down the lights up here so the screen can be seen better?
Just
one.
The other
I
one?
think it's pretty bright.
The other one?
It doesn't make a huge difference, but
The other one?
It's pretty bright.
yeah, just
Reverse.
Yeah, that looks good.
Okay. Well, I feel like I'm right at home. I teach here at Macomb Community College. I was just teaching astronomy earlier today on the center campus. And I teach some of this very stuff. So that's why when I heard a speaker was needed, I thought I can do that. For some of you that have been around in astronomy for a while, a lot of this is going to be kind of tutorial. I mean, you've heard it, a lot of it, but for others, hopefully, a lot of it will be kind of new. So I'm going to spend a little bit of time on ancient understanding of the moon, some of the beginnings of lunar science in ancient times, a little bit on the characteristics of the moon, then a fair amount of time on the formation of the moon, our visits to the moon. Did we really visit the moon? I hope I didn't set myself up for Rotten Tomatoes or things from people who are absolutely convinced that we did not visit the moon. And just a couple of slides on colonizing the moon. I did give a full-length presentation on this topic a few months ago at one of our meetings, and you can watch that if you want. It's on YouTube. Just go to Warren Astronomical Society and put in my last name. And some of my other presentations are there on searching for extraterrestrial intelligence, threats to the electric grid, that kind of stuff. You know, everybody can see the moon, right? And it's big. So people had thoughts about it, typically associating it, like other things up in the sky, with gods. Some societies worship the sun more, some the moon. In ancient Babylon, the moon was their, I guess, their most important god. They thought of it as the creator of all things, way back. This is from an engraving found in Babylon. Here's a king with his servants and the moon goddess. Obviously, here's a crescent moon. The Babylonian calendar, I mean, I'm just picking a few things to illustrate how important the moon was to these people. Their calendar was a lunar calendar. Each month would start when they could see the new moon. Just start to see a crescent moon. That was the first day of the month for them. That means every 29 and a half days they would see a new moon, so it would be their, maybe typically a 30-day month, sometimes 29 days. And that doesn't get you to a correct number of months in the year, so they would add a month every so often to keep the seasons fixed. And it wasn't just the Babylonians that did this. For example, the system of months in the Bible used the Babylonian system. I think in the early parts of the Bible, they call it the first month, the second month, that kind of thing. But after they were in captivity in Babylon, they switched to even using the names that they use in Babylon, like in the Hebrew Bible. There's the month of Nisan, and Nisanu was the older Babylonian term. This is kind of interesting. There are more months, but I just sampled it. And much later, in ancient Greek times, a couple thousand years later, they had a moon goddess named Selene. And in their Greek mythology, so this is Selene, right? She's got the moon here on her head. She's riding on a chariot with a couple of winged horses or something like that. It's kind of hard to tell. But interestingly, in Greek mythology, or Greek religion, or whatever you want to call it, Selene was the daughter of Theia. You're going to hear about Theia when we talk about the origin of the moon, right?
Yep.
That's where that name comes from. Just sampling some other things. This is the Zodiac, and the ecliptic is the path the sun takes through these constellations. The moon also goes through these constellations, the Zodiac. And I pulled this off of a website that has to do with astrology. The sun sign, your sun sign, which is what constellation the sun was in at the time you were born, dictates your zodiac personality, while your moon sign, the second most important influence in your horoscope chart after the sun, represents your emotions, your inner mood. Two together strongly influence your emotional mode of operation. So I'm not personally into astrology, although I was teaching it just today in an astronomy class, teaching a class on the history of astronomy and how it diverged from astrology. And half the class, when I asked, how many of you at least occasionally read your horoscope, half the class raised their hand. So it's a big deal to a lot of people. So in essence, I said astrology, its roots at least, are a religion, and astronomy is a science. And what confuses people is we use the same names for a lot of astronomical objects. Astronomers use the same names as astrology uses. So even today, this kind of stuff, it's not just ancient people that this kind of stuff was important to. Today, in Western society here, it's still important to people, right? So at the same time all of that was going on, a school of thought was developing in ancient Greece, which the word science didn't exist yet. That word's only been around for a couple hundred years. Comes from scientia, Latin word for knowledge. Back then, the closest thing you could find to a scientist was a philosopher. Okay? It means loves knowledge. Philosopher. So there were some Greeks who were philosophers. Some of them went to Babylon and Egypt and soaked up all of their older knowledge that they could, and then came back to what we now call Greece, Macedonia, that kind of stuff. And they further developed that knowledge and developed a way of thinking analytically about physical reality. Because before this, people thought that gods controlled and manipulated everything. And so you couldn't count on causality in a physical sense. you know, you couldn't say, well, I see this always works this way, so it's going to work that way in the future. You could start to think about physical laws that might cause the patterns that you see in nature. It was, well, the gods might be doing it that way right now, but they can do it a different way tomorrow if they want to, okay? But these people started to think, you know, maybe it always is this way. So that was sort of some of the absolute bedrock foundation of science. So here's a picture of the Earth's shadow on the moon. It's a partial eclipse of the moon. And I don't know if you can see it, but the shadow is somewhat curved. Is that obvious?
Yeah.
Yes.
So they realized from that and other things that the Earth was a sphere, and that you're seeing the shadow of a sphere on the moon, and by comparing the curvature of that shadow with the curvature of the moon, you could infer that the Earth was about 4 times as big as the moon in diameter. Okay, so they could get the ratio, approximately, of the diameter of the Earth to the diameter of the moon from that. Kind of slick. Here I showed again. You can also, if you watch an eclipse and time how long it takes from when the shadow of the Earth just touches the moon until it's fully second contact, and then third contact, fourth contact, where it's just leaving the shadow. You can also get information to more accurately get the ratio of the diameters that way. So the size of the moon relative to the Earth was determined by Aristarchus, a Greek philosopher, actually earlier than another Greek named Eratosthenes measured the Earth's size. I'll show that in a moment. Once the Earth's size was known and the ratio was known, you could know not just the relative size of the moon, but its actual size. If you knew the size of the Earth and the ratio of the sizes, then you could determine the actual diameter of the moon. Now, you didn't have to go there to measure it. And you could measure how far away it was by its angular size in the sky. I've replicated those measurements and others that they did. And it's rather accurate, the data that you can get. This, I'm not going to spend much time on it, but this is how they found the size of the Earth. There was a well in southern Egypt where it was learned that on a certain day of the year, the sun shone directly down all the way to the bottom of the well. That was unusual. Normally it would come at an angle and it wouldn't shine all the way to the bottom of other wells. So a guy up in northern Egypt, Alexandria, heard about that. There was a school of Greek philosophers there. So he verified that observation and found out what day it was. And on the same day, he measured the angle that the sun made to the vertical in Alexandria, 7 degrees. He also measured that distance, which was about 500 miles. And so what that told him is this is a part of the circumference of the Earth. If the circumference is 360 degrees, 7 degrees is about 1/50th of 360 degrees. So if you multiply 500 miles by 50, you get the circumference of the Earth.
Pretty cool.
Around 25,000 miles, rather close, you have the right value. And then he already knows that the moon is 4 times smaller in round numbers, so he knows the size of the moon, so he can get the distance of the moon. I mean, I've done all these measurements. They also knew how to measure the distance to the sun. That's a lot harder to do, but I've done that.
Dale, how did you measure the distance? How did you do this experiment?
Just like this.
But where?
Where? What I did is I had a pole in my backyard, and I measured the length of its shadow each day. It gets shorter and shorter as you get to true local noon, which in the summertime is about 1:30 in the afternoon in this area because of daylight savings and because we're on the western side of the Eastern time zone. And wherever you get the shortest shadow, you measure how far it is to the pole and how high the pole is so you can get the angle. So I'd do that every day that I could and plot it as a function of day. As you approach June 21st, the sun is higher and higher in the sky until you get to summer solstice. So you see that, and then we visited relatives in Kentucky. So I took my apparatus along and set it up in their front yard and did that measurement. And I confess I didn't measure the distance between the two. I used a map. I cheated.
You walked.
Yeah, I used a tape measure. And I got the, and so I saw a different angle there. I came back home and repeated that measurement several more times. So then I saw approaching the summer solstice, you see the angle go up, up, up. And then in Kentucky, it was here. And I come back and it's back here. So I could see the difference in angle. It's like 4 degrees. And I knew the distance, so bingo. I had it to within a couple percent or something, which there's no right to get it, to expect it that accurately because the moon's orbit around the Earth is actually elliptical. So it's not always the same distance, right? But if you're in the ballpark, right, that's good. The measurement of the distance to the sun is way more difficult. But I did that too. Put this on the moon. So,
Back to the moon.
back to the moon. So, here's what you see through binoculars or a telescope. You've got these dark, roughly circular areas called maria. That's from an ancient word from Latin. It means sea, or maria is the plural, so seas. And then surrounding the maria are highlands, which is rock, lower density rock. The marias are, they've got a higher iron content, so they look, darker. It turns out it's basalt, it's volcanic material. I'll talk about how that comes to be shortly. You've got smaller whitish craters, and then you've got rays coming out of some of those craters. That material that was ejected when the craters were formed. And as it says here, these big things are from big impact events. And this makes the point that when the moon is closer in its elliptical orbit around the sun, it looks bigger than when it's at the more distant part of its orbit. The difference is 13 or 14%. And the moon has about 6 times less gravity than the Earth, which is not enough to hold down an atmosphere, so there's no air to speak of on the moon. This is a picture taken from a spacecraft out beyond the moon, looking back at the moon and the Earth. Some interesting things. First, it's rather obvious what the size difference is here. Although the spacecraft was closer to the moon than to the Earth, so it makes the moon look a little bigger than it would if you were farther back. The moon, another thing you can see is the moon is darker than the Earth. Its reflectivity, or albedo, the term is about 3 times less than the Earth's. It's surprising because you're used to seeing the moon in the sky, it looks very bright. But that's because you're comparing it to blackness. The moon is actually quite dark, almost as dark as charcoal.
Doesn't it reflect about 7%,
Yes.
something like that.
I keep hearing that, but when I check the numbers, I get more like 11, 12, 13%.
Still pretty dark.
Still low. The Earth's reflectivity, depending on cloud cover, is something like 50%. It's about 3 times higher.
Right.
Interesting thing from that is, you all know how bright moonlight is, especially if it's a full moon. Think how much brighter Earthshine is. Because the Earth is 4 times bigger in diameter, so it's 16 times bigger in area, and it's 3 times more reflective. So it's about 50 times brighter. If you're standing on the moon, where it's nighttime where you are, and a full Earth instead of a full moon, the intensity of Earth shine is 50 times higher than a full moonshine. Hugely bright.
You know, Dale, I imagine you get the sun reflecting off the oceans too.
Sure,
Well,
I
you
mean,
get the clouds
obviously,
too.
the clouds especially.
Yeah.
They're white.
Like I imagine the water would act like a mirror or something in a way too, wouldn't it?
Well, it's
Maybe
not a
not.
flat surface.
Yeah, right.
If it was flat, then most of it would look dark because it would be reflecting light away from you.
Yeah,
It
it's
wouldn't be
kinda-
coming
it's
back
kinda
toward
like-
you, but it's, you know, there are
Clouds.
waves.
So there was a special event going on at that time, right?
At what time?
When that photo was taken? That's a total solar eclipse, right?
Yes,
Wow.
yes.
So that's what it looks like from
So yes,
space,
isn't
but you
it?
can't see the shadow.
Right, because it's hidden by the moon. Here were 3 theories, none of which are believed anymore, about how the moon formed. The fission theory is that the Earth was spinning fast and a chunk of it came loose and flew out into space, went into orbit. The sister theory says the moon formed at the same time as the Earth out of the same cloud of dust and gas, orbiting each other. And in fact, some of the moons of the outer planets probably did form that way. The capture theory says the moon formed elsewhere and came in close to the Earth and got captured. There are problems with all of those theories. They're on the next slide, but I mean, this one, there's just not enough energy to get a chunk of the Earth to come flying. I mean, how often have you seen that happen, you know? I haven't seen that, you know? The capture theory, if here's the Earth and the moon came in from somewhere far away, it would accelerate because of the Earth's gravity as it came in, and then it'd be going too fast to go into orbit, so it would just keep going. You'd need another moon to absorb some of its energy to capture our moon, and then it would have been in a highly elliptical orbit. The sister theory would require that they have a similar composition, but they don't. They do on the surface of the moon and the Earth, but not inside. And you can tell that because the density of the Earth is 5.5 grams per cubic centimeter. The moon, it's only 3.3. So there's something very different about what's inside the two. In fact, the Earth has a large iron or iron-nickel core, and the moon has presumably a small core, but not a very big fraction of its mass. So if they both formed at the same time from the same cloud of dust and gas, how could they have such a different composition? So let's look at the first video. I already have, yeah.
Astronomer Bill Hartman has spent his life studying the events of the early solar system.
The record of the very first part of the Earth's history, all of that is wiped away on the Earth itself because we have erosion and rain and continental drift and continents colliding and mountains coming up and so on.
But all is not lost. There is a record of Earth's earliest days, just not on Earth. It turns out the best place to look is on nearby Mercury and Mars. Their surfaces have barely changed in over 4 billion years, providing us with a unique record of events in the very earliest days of our solar system. They're dotted with ancient impact craters.
You start looking at those craters and you discover that there are not only 100-mile craters and 200-mile craters, there's 600-mile features and some very large objects.
These craters paint a picture of an intensely violent period, of a solar system littered with cosmic debris, where millions of asteroids and comets smashed into the young planets. In the thick of this all-out assault, the Earth too must have been struck.
It was a window into the early history of the Earth, and it made us realize that the Earth itself has had this tremendous history of impacts, enormous impacts that could have really damaged the whole planet. It got people thinking about what would be the effects of giant impacts on the Earth.
Hartmann realised that it wasn't just small asteroids hitting the planets. There were much larger objects too. And the larger the object, the more dramatic the consequences.
So the impact process, it's a wonderful kind of paradox. On the one hand, the small impacts tend to make everything the same, millions and millions of impacts averaged out, but the big impacts give individual personalities to the planets.
Take our planet, tilted on its axis at 23 degrees, with a nearby orbiting satellite, the Moon. We used to think that they'd been born together, until Hartmann proposed a radical theory. The Earth had been hit by something the size of another planet, creating that tilt and the Moon.
The key to our idea was that as the planets grew, you had the finished planets, but you still had leftover bodies. If one of those crashes into the Earth, just as the Earth has finished forming, that can blow out material from which the Moon could form in orbit around the Earth.
Picture the scene. The newly formed Earth hurtling round the Sun, and loads of other planets doing exactly the same thing. Including this one, Theia, about the size of Mars. It was orbiting the Sun at exactly the same distance as the Earth. The two planets were on a collision course. Theia hit the Earth at 25,000 miles per hour, with the force of billions of megaton bombs. The impact ripped off huge sections of the Earth's crust. Billions of tons of debris blasted into space. A ring of red-hot dust and rock formed around the Earth. Over the next 100 years, the rocks and dust slowly clumped together into a ball 1/50th the size of Earth. We call it the Moon. When Hartmann suggested the idea in the 1960s, people found it hard to accept.
Scientists were thinking of everything in terms of slow geologic processes, one grain of sand at a time, wearing down mountains. To think of something as colossal as the Moon forming as a result of a single event was hard for people to swallow.
But then Hartmann got the first real clue that his theory might be true. The Apollo project.
That's one small step for man, one giant leap for mankind.
American astronauts made 6 visits to the moon. They explored its surface, drove around its craters, and brought back 840 pounds of moon rock. For the first time, scientists could find out what the moon was actually made of. The lunar samples had a remarkably similar chemistry to the outermost layer of the Earth's crust. To most researchers, it was an interesting discovery, but to Hartmann, it was vital new evidence.
So you have crustal rocks, you have rocks on the surface, and a big impact comes in and blows all those crustal rocks away. And that material goes into space and forms the moon.
Many scientists were still skeptical. They just couldn't see how a massive impact could create the moon and the Earth as they are today.
I actually had people telling me we should exhaust every other theory first because this was such an outlandish idea.
It was a chance meeting at a conference with astrophysicist Robin Canup that gave Hartmann the breakthrough he was looking for. She was using computer models to study Saturn's moon.
Bill Hartmann came up to me after my talk and asked me, have you ever thought about applying your models about how moons form within and near Saturn's rings to the origin of the moon? And I said, no.
So she tried it. Canup used modelling software to recreate the early solar system. Then she plotted a planetary collision of the kind Hartmann was suggesting.
So we're 4.5 billion years ago, at the end of the Earth's formation. And we're in space, and we're watching as a small planet, the planet on the right, is about to hit the young Earth, represented by the larger planet on the left. The collision takes place, and as we see it hits in a glancing blow. And you can see
I want to point out, I'll resume the movie in a moment. The red represents the core material, which is dense, heavy metal, iron, nickel. Notice that most of the metal winds up staying with the Earth, and it's mostly the mantle, lighter, rocky material that goes out into space.
Talking about the metal of Theo?
What?
The metal interior of Theo?
Of Theia and the Earth, most of that winds up in the Earth, which is why the Earth winds up being more dense than the Moon. Let me just replay that so you can you just back it up?
Sure.
Just
And
a little bit.
is the Earth more metallic than, say, Venus?
Venus has a density quite close to that of the Earth, but the Earth is a little
the collision
more dense.
takes place.
It's
and
a
as we
Mercury
see it
more
hit,
dense still.
It hits in a glancing blow. And you can see the impactor is completely destroyed by the collision.
Theia, the impactor, is annihilated. Earth survives, but only just.
Now this collision is incredibly violent, so violent that there's enough energy to completely melt the Earth. And in fact, at the end of this impact, the Earth is surrounded by an atmosphere of vaporized rock.
Trillions of tons of debris blast out into space.
Here we see part of the impacting planet sheared out into this long arm of material that produces a disk that we're seeing almost edge on in this view. And it's from that disk that the Moon later coalesces.
Canup's model demonstrates that the Moon was probably made of debris from both Theia and Earth. It explains why those Moon rocks were so similar to rocks from the Earth's crust.
So I actually called my colleague and said, you're not going to believe this, but I tried this Mars-sized impactor case with about a 45-degree impact angle, and everything worked. And he said, you better check it again. And so I did check it again and did many more of these simulations, and sure enough, that type of impact is the one that gives us the Earth-Moon system today.
Canup's work was further evidence that Hartmann's radical theory might just be right.
So it was very exciting as Robin did her models and they started to say, yes, there can be moon-forming debris left in orbit around the Earth, and the moon would form from that debris.
Okay, you can stop it there. And take me back to the PowerPoint if you would, please. Dr. Knoop, she tried different sized impactors on the early Earth, hitting it at different angles and at different speeds until she found what worked, what would produce the Earth-Moon system, okay? She didn't know going in how big of a thing hit the Earth, how fast, what angle, until she just tried it until she saw what worked. What worked, as she said, I forget, 25,000 miles an hour or something like that, and about a 45-degree impact and about the size of Mars, okay? That's how she knows. It's just because that gives the right result. Now, what she didn't go on to say in this video is the debris ring that formed around the Earth and coalesced into the moon was not where the moon is now. It was really close to the Earth, probably about 20,000 kilometers from the Earth, which is about 13,000 miles. The moon is now 20 times farther out.
13,000?
Wow.
Yeah.
Yeah.
Inside the Roche limit?
I'm telling you, that's what the numbers say.
Wow.
Oh, it was
So-
already
Certainly,
de-roached.
certainly.
Yeah, this is going to be important in where we're going. Okay, this is important to understand that. So the initial distance to the moon, she thinks, was about 20,000 kilometers. It's now 380,000 kilometers away. Okay, so how did we get from that to where we are now, right? Let's keep going. I just want to pose the question. Get you thinking about it. So, the large impact theory explains some things, such as the lower average density of the moon. She played with the model until she got most of the iron core from Theia, mother of Selene, remember, the moon, until she got most of the iron core to stay with the Earth and just crust from Theia and the Earth to go out and form the moon. Hence, she can explain the small density of the moon. It's mostly rock with very little iron in it. She also then can explain the chemical similarity of the crust of the Earth and the moon. They all came from mixing the crust and mantle of the two planets. And people study isotopes from moon rocks and from the Earth's crust. And one of the ones that's most convenient to study are isotopes of oxygen. Most oxygen is O16, 8 protons and 8 neutrons in the nucleus. A very small amount has 9 neutrons or 10 neutrons. And it's known that, for example, the sun has a different ratio of these. Mercury has a different ratio of these, Mars has a different ratio, and Vesta, one of the asteroids, has a different ratio. So how do you, here's a paper I just found a few days ago from 2014, some Europeans. They say a new series of measurements of oxygen isotopes provides increasing evidence that the moon formed from the collision of the Earth with another large planet-sized astronomical body using lunar rocks from 3 of the Apollo missions. So people are still studying these rocks. So her model explains that, right? It explains it. Then the early moon was initially liquid, so was the early Earth. And after the surface of the moon solidified, it got changed by getting clobbered with a lot of big things. This is the rate of formation of impact craters on the moon versus time over the last 4.5 billion years. There's something here called the late heavy bombardment, where the inner solar system was getting clobbered with stuff. So now we're going to watch an even shorter video about that. Don't lose my place.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye, as a permanent record of its own history, and a glimpse of how craters may have formed here on Earth.
Dale, as I understand it, didn't the moon become tidally locked extremely early after its formation? Do they have an explanation for why all of these basins seem to be favored on the near side?
Great question. We're going there next.
Good, okay.
I think I have about 44 slides, and we're on slide 17. Why don't I suggest that if I can't get done with this tonight, we'll continue it a month from now, since I think you need a speaker for that.
That'd be great.
Talk to our first VP.
I see a smile.
I probably could be talked into such an arrangement.
I hadn't been thinking of that, but I just noticed what slide I'm on, and so let's see how far we get. So I would add, if this was happening to the moon, getting clobbered with this late heavy bombardment, the same thing for sure was happening to the Earth, right? Because the Earth is way 80 times the mass of the moon. So its gravity would tend to suck stuff in that might have just missed the Earth. So if anything, we got hit worse than the moon. And there are two processes on the Earth that have largely erased those huge craters. Plate tectonics where one plate of the Earth slides under the other and melts back into the mantle, is certainly one of those processes, and the other is just weather. Rain, wind, gradually eroding edges of craters away, right? You don't have either of those on the moon. There's no plate tectonics. The moon cooled much faster than the Earth because it's smaller, so its surface, as you take a sphere and shrink it, the surface to volume ratio goes up. So it will radiate away heat much faster if it's smaller. You could also say the heat doesn't have to travel as far from the center of the sphere to the edge in order to radiate. I understand geologists have gone to great lengths to try to find whatever ancient craters, big ancient craters there are on the Earth, and they found a few hundred of them. But you have to do difficult geological studies to find them, those that remain.
There are several within a day's drive, so you can't picnic on a crater's rim.
Okay.
We just go to Sudbury.
I mean, there's a big crater up in Canada, I know, where a nickel-rich meteor hit. It's like, I forget, 70 miles in diameter. And they have big nickel mines there mining that object, for example. Okay, now, one of the issues is, here's the side of the moon that we see, but if you look at the back side of the moon, it looks different, right? I see one halfway decent sized dark Maria, Mare, M-A-R-E is the plural in Latin.
Singular.
Yeah, the singular. Did you study Latin?
Yes.
Figured.
Why
I
are
did
you-
too,
why are you-
but my excuse is it's been a few years longer.
Why are you at all surprised?
So, you know, the question is, why does it look different, right? It's sort of a real basic question. There must be a reason. So they briefly said this in that video. Let's go through it a little more slowly. After the moon's crust solidified, and there's still liquid magma right under the crust, an asteroid comes along and clobbers the moon and makes a big crater, and big cracks going all the way down into the magma, or conceivably it could have punched right into it. But even if it only was big enough to go partway through, lava, dark iron-rich lava, would flow up and fill in the crater and form a dark area. Whereas a smaller object wouldn't hit and cause a deep enough crater to do that. So only asteroids that are big enough to punch through, or essentially punch through the crust, can form one of these dark circular mare. Okay? Well, so what? Why did it happen more on the side of the moon facing us than the other side, right? So, why is there this lunar asymmetry? Now, it turns out that the crust of the moon on the side facing the Earth, the near side of the moon, is thinner than the crust on the far side. The exact thicknesses, incidentally, are not known with high accuracy. How do we know them at all? The way we know them at all is because some of the Apollo missions left seismometers on the surface. And then, after a rocket took the astronauts back up, they turned the rocket around and crashed it into the moon to cause a moonquake, right? And they listened for the the vibrations of that moonquake to go bounce around inside the moon, and from that they could get data on the thickness of the crust. I remember when they did this, okay, back in 1969, early 70s, and they could continue picking up those vibrations for like 45 minutes. The expression was the moon rang like a bell. You don't get that with earthquakes. The reason is the center of the Earth is still liquid, and that absorbs sound waves a lot more. Whereas the moon is essentially, it's dead. It's a solid. And so it doesn't absorb sound waves very well. And so it just kept bouncing around. So they get a fair amount of data from studying those sonic reflections to know what the crust thickness was. Nevertheless, they don't have that many seismometers, so they only have rough numbers. But it's enough to indicate that the back crust is thicker by a good bit. These are some of the numbers I've seen. The crust is thicker on the far side of the moon than on the near side of the moon. So your typical big impactor could punch through or close to punch through the crust on the near side, not on the far side. Okay?
So it's nothing to do with tidal action or anything like that?
Well, there's more to the story.
Okay.
So why was the lunar, you just keep asking why this, right? So where does that get you? Why was the lunar crust thicker on the far side of the moon, right? I mean, why that? So there's two theories on this. One, colloquially, is known as the double whammy theory.
I like this.
Okay? The first idea is that the impact which formed the moon actually formed two moons. Okay? One was big, and the daddy moon, I guess you know, and the other is the baby moon. One was big and forms the bulk of the moon as we know it today, but a smaller moon, also coalesced out of the ejected material, was on a very similar orbit to the big moon. After some time, the two collided. But this would have been a low-speed impact, right? They're both in the same orbit, and sort of more gently came together. If that were the case, the smaller moon would do something like a splash, touching down on the moon and flowing like a liquid over it. This would create a lopsided moon, somewhat, depending on the ratio of the size of the two moons, with a thicker crust on one side than the other, as we see things now. So that's one theory, not the favorite theory, I think, but it's one theory. Here's a sort of a diagram of it. Here's the smaller moon splatting on one side of the bigger one, right? And so you get a lunar asymmetry that way. So that's possible.
It's like a bug on a windshield.
Yeah.
So the smaller moon forms the thicker crust on
Yes.
the far side?
Yes. It makes it different, right? You could think about how far it penetrated in the moon and all that kind of stuff, and what did this wind up being, the thinner or the thicker crust? Probably the thicker, but different, and asymmetry. The other theory, you could call it the Earthshine theory. And here, we're not talking about Earthshine as we normally would think of it, sunlight reflecting off the Earth. We're talking about the Earth being liquid, real hot.
Infrared radiation.
Yeah, well, it would be visible as well as infrared, but a lot of it, more infrared than visible. By some estimates, 4,500 degrees Fahrenheit. You can start to see something will start to look reddish by the time it's 1,200 or 1,300 Fahrenheit. I'm used to thinking centigrade, so. So it'd be really hot, and remember I talked about the moon being initially really close, right? Really close, roughly what you see there, those kind of ratios. Very roughly, ballpark. So the moon would get huge amounts of infrared, mostly radiation hitting it from the Earth because they were so close together. The Earth is big and hot. The fact that the moon was close would have meant the tidal effects would be gigantic. Gigantic.
Wow.
Tidal effects right now can cause tides in the ocean, which are, if there's certain places on the Earth where they're, I don't know, 30 feet high, right? Something like that, I forget exactly. Now we're talking about not water sloshing around, we're talking about liquid rock. So it'd be a bulge on the Earth and a bulge on the moon due to mutual tidal effects. And the moon, since it was close in, would have been going around a lot faster, right? The closer something orbits the Earth, the faster it has to go around to not get sucked in by the Earth's gravity.
How long is a month here?
Yeah, a lunar month would have been something more like a day. Okay, so the tides would have rippled around the Earth frequently, right? It turns out that if you study the physics of that, I mean, and one other thing I forgot to say, the Earth, remember, it was hit a glancing blow by Theia. So it was spinning really fast. By some estimates, the length of a day would have only been 2 or 3 hours. Okay?
So it seems like this theory also helps to slow down the Earth's rotation as
You
well
got
as, as well as giving the moon a kick out of the...
There's something called conservation of angular momentum. Okay? And what tidal effects do is they transfer spin angular momentum of the Earth to orbital angular momentum of the moon. And the effects would have been huge. Okay? So, fairly rapidly, the Earth would have been slowed in its rotation. The length of the day would have been slowed. And the length of the moon would have gotten larger.
Would you say that the moon would be tidally locked at that point?
Yes.
Okay.
The moon would have, because they were so close and the tidal effects so big, it would have very rapidly become tidally locked.
Okay.
Very fast. So, so the moon during this time would have been tidally locked with one side facing the Earth. Think about huge amounts of infrared heat hitting that side of the moon. So now you've got the moon surrounded by rocky vapor. Where is it going to condense? It's going to mostly condense on the cooler side of the moon, which is the far side of the moon. Wow. So the reverse side, the far side of the moon, winds up with a thicker crust. Bingo.
Makes sense.
Now, if you think about those two theories, which one sounds more likely?
Number 2.
Okay. What's wrong with this one?
Doesn't explain the various aspects of the system, like rotation speed, and it doesn't explain how the
near
moon
and far side.
Right.
Well, and you still have the other stuff
Asymmetry.
happening. Even if this happened, you still had it close to the Earth, tidally bound, all the other factors.
You can make this one work, but it's more complicated.
Oh, yeah, wait.
You need a second moon forming.
Right, no.
And a problem with the second moon forming, it seems to me, is this. If it's in the same orbit as the little one as the big one, it isn't going to take long for it to hit.
No.
And if it's only months, in today's months, not the month back then the moon is still going to be liquid. So it's just going to be two liquid balls merging completely with each other.
You don't have that.
Is a concern, right?
Yeah.
You have to work at it to make this small moon survive long enough for this thing to form a substantially thick crust, to where they don't just become one jelly ball, right? Right? Yes.
So do we want to do a few minutes of questions and we'll
Yeah, let's do that
finish the story
next time.
next month?
Cool.
Well, we're halfway through the presentation.
We're doing great.
I'm doing great.
I
have a comment. You can notice that
break your hand
the
ahead of
Mara has
yourself.
less craters than the highlands, even in a
It
telescope.
hurts too.
Markedly different.
I still don't think, I mean, you look at some of these huge basins on the near side, surely, even if the crust was twice as thick, something that size coming in would have gone through to the mantle and you would have these large Maria. I don't like.
Well, there is one large Mare on the other side.
Yeah, there is.
There's one. But
Is
then
that
like
Maria
the near side is
Humboldtiana?
like half.
Well, okay, what's your theory?
I don't have one. I just don't like it.
Dale, is that Mare Humboldtianum that is on the far side?
I don't.
That we can
I
kind
don't.
of see around the...
I don't
No, it's the Sea
remember.
of Moscow.
Oh, okay.
Okay.
Mare Moskovsky.
First
Moscow.
city on our side get to name it.
For another theory, could it be the gravitational pull on the core of the moon by the Earth, just pulling that core, but would have more of a gravitational force on that than the
Is a
thrust?
tidal, yeah,
Pulling
is
it
a
off- pulling it
tidal
off
force
center.
pulling the set.
That used to be one of the theories that, I think that used to be the main theory, that somehow the tidal of, let me find a picture that I can use on this. That somehow, the Earth is over here, and when there's still a very liquid inner core here and the crust, before it thickens up very much, that the differential gravity of the Earth being stronger here than here, pulled this liquid stuff over, the denser stuff over closer to the near side of the moon, and then it solidified. Right?
Mhm.
That doesn't seem to be believed anymore.
Maybe the Maria exists and is just covered up.
Well,
What do you
there's
mean?
lava, I mean, there's...
No, I mean, the large Maria on the front side, on our side, we see them. But maybe they do exist on the far side, but they're just covered up.
How did they get covered
I don't
up?
know, just a guess.
Okay.
There was one theory that I've heard, the reason why the backside of the moon has more craters than the side that faces us is because the side that faces us is shielded from
Yeah.
other objects coming towards it, but the backside is open to.
But it's still
anything
craters
that's
and
going-
highland rock rather than anything deep
Okay,
enough to
right.
punch through to get
Right.
to the marble.
I like
That
this.
shield.
I like
I
this,
mean,
the other
there's a
side.
lot of room out there.
Yeah,
All right, let's
yeah,
do
but-
one last question.
There is no dark side of the moon, really. It's a matter of fact, it's all dark.
I have a mouse pad that differs. Well, anyway, I'll let you wrap up.
Well, I wish we had more time for Q&A, and I'll stick around a little bit. I may have to be up at 3 o'clock this morning doing astronomy, because Io is coming out of Jupiter's shadow at about 3:30.
He's still doing that. Good for
Yeah.
you.
I'm scheduled to give a talk on that in December,
I
I
love
think.
that. That's
So I'm
great.
trying to get data, but man, I hope it's cloudy.
If you're waking up at 3:30, it might as well be clear. I
Must be
mean,
clear, sorry.
So that's why I'm not going to the restaurant, because I gotta get some sleep. But I will stick around for a few minutes if somebody wants to talk about something. And thanks for listening.
all right.